let's look at one more very important idea from the book. This is the last topic in this first chapter on number theory from our wonderful book, and I have no issues in reminding you once again that this is going to be our Bible. And what is this last idea? Which is again a very basic idea. It is the greatest common divisor of two, let's say, natural numbers. Now, you might also be sometimes using the HCF, highest common factor, but I would insist that let us constantly use GCD now to use this concept of greatest common divisor. So, let us just get the basic idea of the greatest common divisor. So, if you have two numbers, you can always write down the prime factorization of both the numbers. So, just to take an example, if this first number is 2 raised to 3 into 3 squared into 7, and the second number is 2 squared into 3 raised to 5 into 5, and if one were to find out, this is the crudest way to find the greatest common divisor. The crudest way is to actually do the prime factorization, but theoretically I feel that it is important to understand the GCD in these terms. Now, if you want to find the greatest common factor, you just need to look at all the common primes. So, for instance, in this case, the GCD will simply be 2 square and 2 cube. You will have to choose 2 square. That is the minimum of these two coefficients. And here 3 square, the minimum of 2 and 5. And this is the end. There is no other common prime factor. So this is the highest common divisor of both the two numbers. Definitely A is divisible by this number. Definitely B is divisible by this number. And this is the highest number that divides both these numbers. Now let's take this in a different way. If D is dividing A and D divides B, this is the requirement to be satisfied by GCD, but then it has to be the greatest. So if any other number divides A and any other number divides B, then E should divide D. If this criterion, if any number is a common divisor of A and B, it should divide D. In that case, we say that D is equal to GCD of A and B. So this is the better way of stating what exactly is the GCD, and this is a crude way of finding out the GCD. So if this is crude, then what is really efficient? What is really efficient is Euclid's algorithm, and all of us have learned how to find out the GCD quickly with the help of the GCDs, with the help of the Euclid algorithm. There is no issue there, but let us write down one more thing here that is worthwhile. What is the least common multiple? In the case of the least common multiple, you have to choose, instead of the smallest, you have to choose the greatest. So this is going to be 2 cube, and then in these two you have to have 3 raised to 5, and you should also include the numbers which are not there into 7 and into 5. So this time, in this case, you chose the minimum of the exponent. In this case, you choose the maximum of the exponent. Now this is clearly a multiple of this number. This is also a multiple of this number, and this is a common multiple, which is the least common multiple of both A and B. Now, just the way we have written down the GCD and the LCM, you can very clearly see that this is GCD into LCM is actually equal to the product of the two numbers A and B. Now this is a very neat formula and may not be so easy to prove, though it's an important fact that you should remember. Now what I want you to understand from this is that if you have an efficient algorithm for the GCD, then finding out LCM does not require another algorithm because of this nice formula of GCD into LCM is equal to AB. So with that, we have understood what is the GCD and the LCM. We have looked at this nice formula, and this is the nicer way of describing what exactly is GCD. This is a sort of definition that will help us in proofs. So with this background, let us now look at Euclid's algorithm from the problem solving point of view. It is given beautifully in the book, and there are two versions of the algorithm. Now both of these versions are described quite well in the book. Now I shall quickly go through them exactly as it is in the book. The first algorithm, which is not the efficient one, simply says that the GCD of two numbers, if A is greater than B, is also equal to GCD of the smaller number and A minus B. And this you can use repeatedly to make the numbers smaller and smaller till it becomes small enough for you to easily tackle the problem. So I'll just use the same example that's there in the book. This is the first algorithm. Now let us use this algorithm to find the GCD of the two numbers that are mentioned in the example in the book. Now instead of using the crude prime factorization of these numbers, we shall simply use this algorithm repeatedly, and the whole idea is that the steps are repetitive. Take the smaller number 164 and take the difference between the two numbers. In this case I can see that it is 123. Yes, I've got this right. Now the point is that let us just repeat the algorithm. The numbers are still not small enough, so I write the smaller number 123. And now the difference between them is 41. Now I continue to do this, and this time the smaller number is 41, and the difference between these two numbers is 59, 69, 79 plus 382. And now it is pretty apparent that the answer for this is 41, and you can see that the algorithm has helped us to find the GCD. Now before we look into Euclid's second algorithm, which is really the powerful one, let us try to see why. It's very easy to explain why it works. So let us have a look at that. So let us quickly give a proof of why this algorithm works, and in other words what we have to prove is that this particular statement. How do we prove this? So let's look at it. We have to prove, the way we will prove it is, the way we will prove this statement is, if D belongs to the LHS, that is D is a common divisor of A and B, then I think this is not well written. If D is a common divisor of A and B, then D is also a common divisor of B and A minus B. Now, just want to point out one minor thing. This statement alone does not complete the proof. We should prove the reverse also. That is, if D is a common divisor of B and A minus B, then D is also a common divisor of A and B. And you can see that both these statements are actually going to be very easy to prove. Now, what we really shown is that all the common divisors on the LHS belong to the common divisors in the RHS, and all the common divisors on the RHS belong to the common divisors on the LHS. In other words, the bag of common divisors on the left hand side and the right hand side is same, and that would automatically mean that the greatest in that bag on the left hand side is also equal to the greatest in the bag on the right hand side. So let me prove this one statement, and then we shall not necessarily prove the second statement because it's very similar. So let us see what I am going to try to prove. If D divides A and D divides B implies D divides B and D divides A minus B. Well, D divides B is already given, so there's nothing to prove here. All we need to prove is that given the left hand side, D divides A minus B. So let us see what this means. This means that some constant times D is equal to A, and this means that some constant times D, some natural number times D is equal to B. Now what is A minus B? A minus B is nothing but K1B minus A2B, and this clearly means that A minus B is equal to D times K1 minus A2. So we have an integer here and an integer here, and clearly A minus B is a multiple of D, and this means that D divides A minus B. So proving the reverse statement, the converse statement, that D divides B and D divides A minus B implies D divides A and D divides B is equally easy. So let us not spend much time on this. Rather, let us mention the second Euclid's algorithm, and then let us put a close to our discussion on Euclid's algorithm. So let us look at the second algorithm, which is quite important because it is a more efficient algorithm. Here what it says is GCD of AB is equal to GCD of the smaller number B, and now we have something called R. So what is R? What you have to do is you divide the bigger number by the smaller number and write it such that A is equal to quotient times the divisor plus the remainder. Now, we're really not interested in Q, we're interested in zeroing down on the remainder, and this is what is R. So finally, how easy is it or how difficult is it to prove it? It is the same proof as before. All you need to prove is if D is a common divisor of A and B, then D is also a common divisor of B and R. It's very easy to prove this, but remember, you must, to complete the proof, you must also prove the opposite direction, and the opposite direction is if D is a common divisor of B and R, then D is also a common divisor of A and B, and that is also equally easy. So with this, we have proved Euclid's second algorithm, and now before we close this lesson, let us solve one or two problems. So let's just go ahead and solve one problem from the book. Let me see what might be a good problem. Okay, let's try to prove this. Find the GCD of 2 raised to 100 minus 1 and 2 raised to 120 minus 1. Okay, so let us just use Euclid's algorithm for 2 raised to 100 minus 1 and 2 raised to 120 minus 1. As you can see that these are very big numbers, and Euclid's algorithm will be pretty efficient to find the GCD of these two large numbers. So let us use Euclid's second algorithm. Now this is the bigger number A, and this is the smaller number B. So this will be equal to GCD of B and R. So I have to find the remainder when A is divided by B. So let us actually divide A, that is 2 raised to 120 minus 1, with B, 2 raised to 100 minus 1. So let's actually divide and see what is the remainder. This is 2 raised to 20. So this is going to be 2 raised to 120, and then minus 2 raised to 20, and then there's a minus 1 here. Okay, so this plus this, so this becomes 2 raised to 20 minus 1. Now you can see that 2 raised to 20 minus 1 is less than the divisor. So this is indeed the remainder for this particular step. So now this is equal to GCD of the smaller number, which is 2 raised to, the smaller number is 2 raised to 100 minus 1, and this is the remainder, 2 raised to 20 minus 1. Okay, so we have proceeded one step, and now I have to repeat the step. So for that, I have to this time identify what is the smaller number. The smaller number is, in this case, is 2 raised to 20 minus 1. So this is equal to GCD of 2 raised to 20 minus 1. And now I have to divide 2 raised to 100 minus 1 with 2 raised to 20 minus 1. So let's try to do that. This is 2 raised to 100 minus 1 divided by 2 raised to 20 minus 1. So let me try this. This is 2 raised to 80. So this will give me 2 raised to 100 minus 2 raised to 80 minus plus 2 raised to 80 minus 1. Now 2 raised to 80 minus 1 is not less than 2 raised to 20 minus 1. So this cannot be the remainder. So I have to continue. 2 raised to 60, and that gives me 2 raised to 80 minus 2 raised to 60, and then this will become 2 raised to 60 minus 1, and it's still not the remainder. So 2 raised to 40, and now this is going to be 2 raised to 60 minus 2 raised to 40 minus 1, and this, and therefore now I should continue with this. It becomes 2 raised to 40 minus 1, and this time I have to continue 2 raised to 20, and this gives me 2 raised to 40 minus 2 raised to 20, and again minus plus, so 2 raised to 20 minus 1, and this time we have a very interesting situation. 2 raised to 20, the remainder is 0. In other words, the remainder is 0. Now what this means is that 2 raised to 100 minus 1 is divisible by 2 raised to 20 minus 1, and that would mean that the GCD is simply 2 raised to 20 minus 1. So here you see that we have used Euclid's algorithm, and with the help of Euclid's algorithm we have been able to find the remainder of these two large numbers in a few steps. So there are a few more examples which are very interesting. So I urge you to have a look at these examples, and this actually completes the chapter number 1 or the 2 or 3 important chapters on number theory in this book. So please go ahead and finish this chapter, and we'll push on to the next chapter very soon. All the best. See you. Bye.